Then we see how to overfitting. Okay, what the authors of this training data and compare with the average energy of. So in the validation set also you have free energy computation. You calculate the average free energy of the validation set. Then you compare these two. Okay, and you check if the gap between these two average, okay, is very low, then there might chance of overfitting. Okay, then how to assign the initial values of the weights and bias. So what we do, use small random values for the weights chosen from a zero mean Gaussian with standard deviation 0.01. But initially choose very small random values of weights between from a normal Gaussian normal distribution. You can choose some random values. Initially set the hidden bias as 0, and then each iteration you have to update the bias. Okay, and set the visible bias as log of pi divided by 1 minus pi, where pi is the proportion of training vectors in which unit I is on. Okay, so so log pi is the proportion of the training vectors in which unit I is on. So unit I means it is a hidden unit I. Okay, so I is on. So I is on means the value is 1. So suppose if you have an input layer, it is visible biases. Okay, in the visible node you have a binary pattern, say 1010. So if how many ones are there, you just find out the proportion and take the logarithm of this formula. Then you can give the initial visible bias. Okay, so then the point is this: how to choose the number of hidden units. Okay, so there are the other methods also there to designing the number of hidden units, but the point is here you have to estimate, first find out how many bits it would take to describe each data vector. That you can use log to probability of the data vector. Okay, minus log to p, that N3 formula. So how many bits you need to describe each data vector, then multiply that value with the number of training cases. So how many training examples you have, you just multiply with those training cases, and then you use a number of parameters that is about or in order of magnitude smaller. So then you find some number that is very less in comparison to your input size. Other methods are there. For example, if you have, just I told before, you have a previously some, you have mixed type of data, labeled and unlabeled. Then from labeling data, you can decide how many hidden units, hidden nodes you can create from the labeling data, and then use those things to predict the unlabeling data. Okay. Another point here that what I have to say here, that here overfitting. So the point is here overfitting you can also, if this is one strategy, you compute the average free energy. Another strategy you can avoid. So if you have multiple hidden layers, just some questions are asked, what is the advantage of multiple hidden layer? So all of you know that we are using multiple hidden layers to avoid the training loss. Okay, so if you have too many multiple hidden layer, it leads to sometimes overfitting. So that time we may reduce the hidden layer, but it is not always true that if you have more hidden layers, you will get best result. Okay, so another point we can do using that overfitting, that we can do some regularization. Okay, so doing those things we can avoid overfitting. Then the point is, what are the different types of functions we will use? So different type of functions we can use. So already we have, I told you, they are sigma function or submat function, or you can you have a Gaussian visible units, Gaussian visible and hidden units. Okay, and rectified linear ReLU function also you can use as activation function. The point is here I told you, let us come to this original diagram. So here, I told that x are 1, 0, 1, that Bernoulli follows Bernoulli distribution. So there are several cases, okay, that formula little bit change. If you have input, visible layer input as Bernoulli distribution and output as Bernoulli distribution. And the formula will change if your input as Gaussian distribution for continuous variable. For continuous variable, you can take this as Gaussian distribution and the output as Bernoulli, or you have Gaussian to Bernoulli, okay? Gaussian distribution to Bernoulli distribution. So that time your formula, that means the contrastive CD algorithm, okay? So this algorithm, what I intend to say, this contrastive divergence algorithm, this algorithm little bit changed because your distributions have changed, so the formula, everything little bit changed, okay? But the idea is KL divergence. This is nothing but KL divergence. So then another point, what is the parameters here involved? Initial values, weights, then another choosing the number of hidden units, and overfitting, and activation functions. So I think this is all about a brief overview of this restricted Boltzmann machines. So now 5 to 6 minutes, I will take the questions.